Yeah. Không còn hiểu với đồng rất nhiều giới trẻ thôi.
Tới nha này không kia
Em được chưa?
Welcome to the final lecture of the annual meeting. It's my pleasure to introduce Professor Phan Duong Hieu from the Institute Polytechnic de Paris. Sorry, I don't speak French. Professor Hieu is a professor and head of the cybersecurity cryptography team at Telecom Paris. He obtained his PhD in cryptography from the École Normale Supérieure. He worked on decentralized and privacy-preserving crypto system, as well as breaking into your credit card.
Maybe, but I not tell you. I can break it.
Okay. Well, if you have a quantum computer, right? Okay. He's actively involved in the cryptographic research community through the International Association for Cryptologic Research, IACR, serving on the steering committees of both the IACR Asia Crypt and IACR Public Key Cryptography. Professor Hieu has been also very active in developing and fostering collaboration between Vietnam and France in the field of cryptography. And today, he's gonna talk about the the love story between Alice and Bob. Actually, he's gonna talk about the cryptography under the two-view principle. Please.
Thank you. Thank you for the nice introduction. I really like the love story. So I will try to explain cryptography by from my personal view. And so also thank you very much to invite me. I'm very happy to be here to give a talk at the annual meeting of VIASM. So here's an outline of my talk. First, I will present some key cryptographic primitives under my personal views. And that I call the two-view principle between mathematical and computational views, between the static and interactive proof, and between the security and learnability. And then I try to discuss some complex application and how we can protect the privacy in these applications, such as e-voting. And then we try to consider strong adversary models, like we say quantum attack. And finally, I will address some emerging security threats from advanced data relation technology that does not follow our formalization. They can take our secret key, etc. And so that gives the need to reconsider the security model. And for this, we introduce a new model that we call anamorphic cryptography. So now the most important objective of cryptography is to assure the secure communication. And now we try to, I will give a personal view on this. And so in mathematics, you know, so if we have two algebraic structure, and if there is an isomorphism between two structures, then we say that, oh, they are the same, just renaming the object. So, and for example, if you consider one of the simplest structure in algebra, ZQ for a prime Q. So it's a very simple finite things, and we can do everything, multiplication, addition. And now we consider a second structure. Suppose we have a cyclic group of we can consider the multiplicative group of the same order Q. So the element is 1J, J2, etc. And we can define also two operations on this structure. That's called the addition and multiplication in the box. We just do the addition and the multiplication on the exponent. And so if mathematicians say that they are the same. So just we have an isomorphism phi that send x to g to the x. And so everything in the first structure, and you can do the same in the second structure. However, now if we add a computational view into the structure, the things become very interesting. Because in the first structure, everything can be efficiently computable. But in the second structure now, in many structure, like if we choose J like a subgroup of finite things, or a cyclic subgroup of the group of point of the elliptic curve, then phi is easy to compute. But the inverse is very hard. And actually, no efficient algorithm can compute the inverse of phi. That's called the discrete logarithm. Given g to the x, to compute x is hard. And so it means that now in the second structure, the multiplication between two elements is hard. It's not easy to, given x and y, it's very difficult to compute the multiplication of x and y, and that's called the computational Diffie-Hellman problem. And so if you can solve the discrete log, and you can go back to the first structure, and then we can compute this. And so the computational Diffie-Hellman cannot be harder than discrete log problem. And these two problems are considered actually very hard to compute. And now the nice thing is that in the second structure, this operation is hard to compute. But if we have additional knowledge, it means that if we have a small x or small y, then we can do this operation. It means that now, and very interesting thing is that x and y are generated, can be generated in local. It means that I myself can generate small x, and you can generate small y. And so we can do this operation, but all the other people who don't know x or y cannot do this operation. And so that gives something like the revolution of cryptography, because now we can set up the key, the common key, as the multiplication of x and y. And so only the insider, we say insider who generate in local x and or y, can do this operation and can compute the common key, and they can use the key to hide the message. And so in some sense, the insider have a mathematical view of the structure, and the outsider, the adversary, have a computational view of the structure. They cannot do the operation, but the insider can do the operation. And so the insider can do the operation without the need to change any secret before, because they generate X and Y in local. So that gives the revolution of cryptography that we can establish the secure communication without sharing any secret. That is very important, because that's given by D.P. Henman in 76, and we know in many thousand years before, to establish the secure communication, each pair of people need to share some secret beforehand. And so here, so the revolution is that we don't need to share anything. We generate something in local. We can do the operation of the structure, and all the outsider cannot do it. And after this, this can be turned into a public key encryption easily. So now the secret key is X, and I publish the bit X is G to the X. And now to encrypt is something like we generate on the fly a random element Y, and we do the operation X multiplied by Y, like the session key, and we hide the message M. And so we are the insider, we know X, we can do the operation X multiplied by Y, and then we can get the math, and we can get back the message. So that's the idea, that the insider have a mathematical view and outsider have a computational view. And insider can do something that the outsider, the adversary, cannot do. And so that gives the public key encryption. And so,
Sorry, so how about the G? The G is the public information.
Yeah, the group J is public. Everything is public. The structure is public. Mathematical structure is public. But in this structure, if you don't have information, you cannot do the operation. But you are insider, you generate the element, then you can do the operation. And the possibility to do the operation help you to establish the common key. And so now, the second most important goal of cryptography is authentication. So we can exchange the CQ communication, but how we can convince the other one that the message comes from me, but not another guy. And so how I can identify, for example, if I want to go to a secret love story club, I need to prove my membership. If maybe I have a password, and the bodyguard can ask me the password. If I give him the password, he say, oh, you have a password, you can get in. But it's very dangerous, because this bodyguard can get my password and give to another boy, and he can go into the club. So that gives the need how we can prove my identity without leaking any information. And so that's give another thing, interesting things. For example, here is, I know Angel like very much French wine. And so he can distinguish two kinds of wine, Bordeaux and Rhone, for example. And now he claims that I can distinguish these two wines. And so mathematically, how he can convince you that he can distinguish this. So mathematically, so he have a system of axiom and reduction, etc. And so he write a very long proof, step by step, follows the formalization, and until the last step is the claim. So it's a proof. So maybe if I know something, I can be convinced. But if I don't know anything about the why, so maybe I'm not convinced. And the second thing is very dangerous is that I can bring this your proof to show to another one that I can also distinguish these two why. And so in fact, that gives can we avoid this problem? And that gives the notion of interactive proof. And this, by Shimon, he says that a proof, now we need to change the notion of proof. And now a proof is whatever that's convinced me. And now he can say, we can do interaction. So it's very important, like what he said yesterday. So the human is very important, the human interaction, for example. And now with the interaction, how we can give a proof, a sample proof. And Joe wants to convince me that he knows how to distinguish these two Y. And so it's a very easy game. So I secretly take one of the two Y and I give to Angel. Angel taste and say, oh, this is Bogdo. Oh, it's correct. The second time, oh, he say it's wrong. Okay, so if you repeat this 100th time, and if every time Angel gives the correct answer, yeah, Bo he's wrong and he can distinguish why. And the probability that he can cheat if he don't know how to distinguish why is 1/200 is something like you can win the lotto 1,000 day consecutive, something like that. And so that's if I accept the very negligible probability that the proof is wrong, then we can have a very simple proof. And the most important thing is that this proof, the verifier was convinced about the claim, but after the interaction, I gain no any information. So it means that the interaction with Angel does not give me more knowledge, because myself, I choose the Y, and so the answer I chose is just correct. That's the Y I choose. So that does not give any more knowledge. And another way to formalize this is that I myself can simulate the interaction in such a way that the outputs look exactly the same distribution with the interaction with the prover. And so that gives the notion of zero knowledge proof, that the verifier was convinced about the claim and gained no knowledge. That's very important. That solved the problem before. I do not need to give my password. I only convince the bodyguards as I member of the group that my ability to do something here is to distinguish the Y. And this also gives a duality, some kind between cryptography and machine learning, because you see the interaction in all the cryptography primitive, the security is always formalized as a game between an adversary, here the verifier, and the system. And the adversary try via the interaction to get more and more data. And the question is that after the interaction, if the adversary can gain something, can learn something. And a scheme is secure in cryptography means that the adversary cannot learn something meaningful. It means that the problem is unlearnable. So the adversary cannot learn. So it means that somehow if cryptography continue to exist, then there will be the problem that machine learning have no advantage. And so that is interesting that after that, this Gondry, Mikali, and Witteson show that all the problem, NP problem, so the NP problem is class of all the problems that we can verify efficiently. And so it means that it contains all the meaningful problem, because if a problem that we cannot verify the solution, then it does not really make sense. And so it means that everything we can verify efficiently, we can verify without gaining any knowledge. So there is zero knowledge for all the problem under the existence of one-way function, like the kind of functions that one direction is easy, but the inverse direction is not easy, like the exponential function. And so here is like a game, but now I try to give a concrete example that also gives the scheme that we are using today. So come back to the discrete log. Now, in reality, in the system, so we have a cyclic group J, and I give, my password is the X, and I give H is a G to the X at the public key. And so now, if I want to go to the secret club, I need to show that I know X, such that H equal to G to the X. And so if I give X, so verifier can verify easily, but I lose my password. So how I can prove that I know X without giving any information about X? And so we can do this under the discrete log assumption. And so now we have a two element, G and H. So we can create a space generated by these two elements, J and H. And so scalar multiplication like in the exponent. We do the linear combination, linear algebra in the exponent. And so linear combination of two elements is just a G to the H, A, H to the B. And so now what is interesting, also interesting is that distinguishes also the mathematical view and computational view. In the mathematical view, then H is a G to the H. H is a G to the I. So it means that H can be represented by J. And so they are like dependent. So the space generated by J and H is just one dimension. But now in the computational view, if we consider like in the constructive mathematics, if we cannot compute something, we cannot say that is true. And so it means that if we cannot give X, we cannot say that H is dependent on J. And so it means that now in the computational view, J and H looks like two independent vectors. And so the space generated by J and H look like a two-dimensional space. So now I want to prove that I know X is equivalent to say that I live in the one-dimension space. So the insider with X lives with the mathematical view, lives in one-dimension space, and the outsider without X lives in the two-dimension space. And now so the problem becomes easier just to prove that I live in one-dimension space. How I can prove that? So the insider is a prover. So two vector is dependent. So it's a one-dimension space. And here in the computational view, two vectors are independent. And so they generate a two-dimension space. And so now, if I live in two-dimension space, given any vector R, I can only have one representation in the basis of J and H, like I equal to G to the H, A, H to the B. Because if I have two representation, A, B, and A prime, B prime, that means that A plus B I equal to A prime plus B prime I. And then I can compute I. So it means that if I don't know X, it means that I only have one representation. And if I know X, then if I know X, then I can have many representations because I just take a coefficient for H, B, and I can compute A like X minus B, R minus BX. So it means that now I will convince you that I know X by showing to you that for an element R, I can have many representations. But if I give you many representations, more than one representation, you learn X. So I only give you just one representation. And how I can give you one representation, but you are convinced that I have many representations. That's become an easy game. So I give you R, and you give me the coefficient of H, a random coefficient of H. And then for a random coefficient B of H, if I can give back to you, I can complete with a coefficient A of J. That satisfies that R is a representation of J and H. Then you're convinced because you say, oh, for any B, for random B, you can give me A. So you need to have many representations because if you have only one representation, then you can only answer to me if I give you the correct B. But this happens with the probability 1 over Q. And so it's negligible. And so it means that here, just a very simple protocol that I can convince you that I know X without leaking any information about X. And what is interesting from this protocol is that the challenge could be random. And now, if you replace this random challenge by something depending on the message, then the magical thing happens that this becomes a digital signature. So the signature is that I want to sign on a paper, on message, So I want to prove that only me who can sign on the message. And now I just give you the zero knowledge proof. My proof of knowledge depend on the message. And everyone can verify, thus give the signature of the message. So I take this proof and anyone can verify. And because the challenge depend on the message and on the R, I cannot cheat. Because if the function H is supposed to be a random function, and in the proof is called a random oracle model. And so that gives this digital signature. And this signature is called the Schnorr signature. And Schnorr signature become the basis for many signatures we have been using today and later on with, and also, unfortunately, Schnorr passed away last month. So I may dedicate this slide for him. And so, and here you can see that from zero knowledge proof, from something very looks like theoretical, we can turn on something very useful in the real life. And this transformation, that's called the Fiat-Shamir transformation. And so we can see that, again, this distinguishes the two views, the mathematical view and the computational view. With mathematical view, we can do the proof, and the computational view, we cannot break, cannot cheat, but we can verify. And so after the invention of encryption and signature, then there are more and more advanced property on the signature, randomizable signature, aggregate signature, threshold, group signature, and also on the encryption that give many kind of functional encryption or fully homomorphic encryption. And all these kind of primitives help us to do many important applications in the big data and AI, because we can protect the privacy by doing the computation over encrypted data. You can encrypt all our data and delegate to the server to this computation over our encrypted data. They give us back the encrypted result, and only us who have key can decrypt. And there are many also interesting examples, like actually the big project for deepfake to combat deepfake. So the way is to, for example, each reporter who take a picture in the world, and so in the camera, there is a secret key in the temper-resistant memory. No one can change. They can sign the picture, and then when the picture put on the media, we can verify the signature. But the problem is that the picture where the reporter take is very huge, but on the media it is small. So we need advanced property on the proof, on the signature, in such a way that we can modify the original picture, which only allow operation into the small picture, like we do the crop, cropping the picture, etc. It means that we define the allow operation, and we need to define advanced property for signature and proof in such a way that when we modify the picture with allow property, then we preserve the signature, or preserve the proof. And so we can publicly verify the picture on the media. And if the signature or proof is not correct, we can say that it's a fake image. And also, very important thing is the privacy in voting. So, and I would like to talk a bit about this. And the challenge in voting is that how we can achieve both privacy and public verifiability. The privacy assures us when we do the tallying, no one can link a ballot with some person. And all of these procedures need to be verified publicly. And so a framework is very famous, is a mixed server. The mixed server is now, here is the input ballot in the encrypted form. And so that no one know who I voted for. And then the mix server will now randomly permute the encrypted vote. And we need many server, and so at the end, we don't know the link. If one of the mix server is honest to do the job, to randomly permit the vote, then at the end, we don't know this ballot correspond to which person, and then we can jointly, this tallying can be done in distributed way. And so technically, this requires us, the mix server need to use an encryption which is randomizable from the ciphertext C to randomize this ciphertext. For example, so that we cannot see this ciphertext, we cannot detect if correspond to which ciphertext. And then the second thing is very important is that because this is the encrypted form, so no one knows what the mix server do. So the mix server need to provide a zero knowledge proof that the content in all of these outputs is a permutation of the content in this input ballot. And so that gives a global zero knowledge proof on all the ballot. And if you see if there are 10 million people, the zero knowledge proof on this huge number of ballots become very expensive. And in fact, in France, so in 2018, for the education, national education, they apply this method. And there are 400,000 voters. And they do with just one mix server, but the tallying, the verification took days to verify. It's very costly. And this is not even half of the million. And now you can see if there are 10 million, the problem become impossible. And so that's why in 2020, with Phan Duong Hieu and our PhD student, Chloe Eban, we propose a new method to avoid the zero knowledge proof on permutation, on the whole permutation. And now the input for the mix server, not only the ciphertext, but also the signature of the user and the certification that the user has the right to vote. And now we can randomize everything. No, not only the ciphertext, but also the signature and the certification. And so in the output, if this is valid, it can be verified by the signature, then we are sure that this comes from one of these ballots. And so by the validity of this randomized signature, we can prove that the only way the mix server do is to randomize. And we can avoid some other problem that the mix server collude with the user to introduce new vote by binding on the input and on the output. And this way you can, in fact, multiply on the vote in the input and on the vote in the output, and that form a Diffie-Hellman tuple. That is the form of j to the x, j to the I, j to the xy. And we only need one zero knowledge proof for 4 elements of this form. Then we can show that this can be done. And so we avoid the global permutation problem. And that is interesting that now this method, there are many current development of this method. And in Japan, the NTT proposed an improvement of this method, and they try, Abe, the chief scientist of NTT, they try to apply this method for some kind of national election. And also this is interesting enough that David Phan Duong Hieu quit ENS to develop this kind of voting, aiming for the national campaign in the next year. And also Telecom Paris, our group improved this method by moving on the job of mix server offline before the voting are cast. Because one of the problems with the voting is that after voting, if with some polling, some parties think that they will lose, then they don't collaborate for the tallying. And here we show that everything the authority can do can be done offline before the voting are cast. And so at the moment the voting are cast, then everyone can do the tallying publicly. And so that avoid any problem, and that's moving on the task at the offline. Okay, so that's and now I give the impression that cryptography can do many things. Advanced property can protect the data, but how about new adversary model that we call quantum? And so the idea of using quantum, I don't know, that's high the title. Okay, here the quantum, I explain quickly the quantum speed up via detecting hidden structure. This is a Shor algorithm. The idea in the Shor algorithm is that if a function f is periodic, if there is period R in such a way that f is spread R equal to fx, then we can recover R. We can recover the period. So with quantum computation, the nice thing is that we can generate a quantum state on the superposition. It means that you can put on the first register x and second one fx on all the value of x on the superposition. It means that now if we do the measurement on the first register, you can get x, then the second register need to be fi. And now, because f is periodic, we will measure the second register. We measure this second register and obtain y, which is f of some x0. And so we know that now the first register will contain all the value that fx equal to y. But because the f is periodic, then it will keep all the value x0, x0, 0 plus r, x0 plus 2r, etc. And now if we do the measurement on this register, we will recover one of these elements. But because x0 is random, then we get no information. So because this is period by the space R, so we can change the time domain into the frequency domain. And so now, because in quantum computation, you can apply any unitary transformation, then now we apply the Fourier transform. Then you can change the time domain to the frequency domain. And because it's periodic by R, the frequency here, we can keep all the multiple of n over R. And so if we measure this register, we will get the multiple of n over R. And now it's 0, it disappears. It's only keep only information on R. And after some repetition, we can recover R. And so why this works for discrete log? And for discrete logarithm problem, then you can define a function like linear combination like before on J and H. Given J and H to the G to the X, and the goal is to solve the discrete logarithm is to compute X. And now we define function fab like G to the X, H to the B. And so the kernel of this function is generated by X and minus 1. And so we can see that X minus 1 play exactly the role of the period of this function. Because if you add a multiple of X and minus 1, then the function doesn't change. Which means that X and minus 1 is indeed like X like period of this function. And so by quantum computation, we can compute this period. And so we can compute X. And so this problem is, this subgroup is hidden because we don't know X, but with quantum computation, the period finding problem here can be generalized to the class of hidden subgroup problem, and you can detect the hidden subgroup, and you can compute X. And that's the idea to break the discrete logarithm by quantum computation, and also for the factorization, we can do the same trick. And so should we build quantum computers? So to build the quantum computers to solve this discrete logarithm remain extremely expensive. You can see here, to generate this register, if the domain n in the discrete logarithm, we use actually the n is about 2000, at least 2000, 2 to the 2048. And so it means that we need log n qubit for the first register, log n qubit for the second register. It means that we need about 4,000 qubit. And here is the 4,000 logical qubit is error-free. But in the quantum computation, we need to do the measurement, etc. We need to maintain the state. And so there is always error. And we need to do the error correcting in the quantum computation. And it's totally different in the classical way, because in classical way, we see the bit. And in quantum, until we do the measurement, we don't see anything. And so doing the quantum error correcting error in quantum computation costs very expensive. It requires thousands of physical qubits per logical bit. And so it means that we need a machine with millions of physical qubits. And actually, the record is a machine with some 100 qubits. And so 25 years ago, when I was a master's student, and I took the quantum computation courses, it's fascinating, amazing courses. The professor predicted that in 20 years, maybe we will have a quantum machine. And now the same courses, the professor also predicted that in 20 years, that may have a quantum machine. And so you can see that 20 years is a fixed point. And so my position is that they're very expensive, it is unclear. And so Vietnam should not invest in the cost of building this quantum machine. Theory is very interesting, can do theory, but should not hugely invest in building this quantum. And so the people may ask me, oh, if you don't do the quantum machine, then it happens. If the professor is right, then all our system will be broken. No, that's totally different. In contrast, achieving quantum CQ communication is possible without doing quantum machine. And we repeat. So the quantum break my slide. Oh.
Maybe someone really wants.
Oh, sorry. Oh, I don't know what happened. It's like okay, so why? Because again, we repeat that the insider, we are the insider who design the cryptography scheme, and we have the mathematical view. All the operations are easily to be computed, and the other three play the outsider, and in their view, it's a computational view. And so in the computational view, they want to solve the problem, to break the scheme. And now it means that with quantum computation, that give the outsider a new power. And so, but it does not contradict that we need to change our view. It means that now the goal of construct post-quantum to achieve a post-quantum security is just to find very simple mathematical structure in this world, no quantum, in such a way that the outsider even enhance power with quantum computation cannot break that problem. So it means that post-quantum security is just classical. Do not need quantum machine. We do not, why we need to have quantum here? We do not need quantum here. And so the post-quantum is to find a simple mathematical structure to separate, again, the insider and outsider view. And so here is an example, there are many candidates, but here is a nice candidate. So come back to N-Gaman. N-Gaman, we repeat that we do some kind of linear algebra in the exponent, and now for post-quantum we do classically. And so in N-Gaman, so we repeat that we have a cyclic group generated by J. And now we will replace J by a matrix A. And the secret key in N-Gaman is X. And now we replace by vector X. And the public key is a G to the X, and now we just do X times A. And to encrypt the mask, we encrypt with random S, we do G to the S, and now we do the same thing, A times S. And the mask in n-gamma is just G to the X times S, and now we do, here we multiply X by this side. So we have the same variant of n-gamma that we presented before. But of course, we can encrypt, but we can also decrypt. But the actual scheme is not secure because you see, if we give A times S, it means that S is unknown. And if you give too many linear equations on S, then by linear algebra, by Gauss elimination, we can find out S. And then you can decrypt. But the very interesting that now, if you give A times S, but if we add some noise, so it means that we give a system a linear equation, but for each equation, we just add a noise. Then the problem of recover S become very hard. And so that is called the learning with error problem. And now we add noise here. So in the description, we multiply X with noise, then we need to add an additional term, which depends on X times noise. So X should be small. Otherwise, X times the noise is big, it cannot decrypt anymore. And so, but fortunately, for X is small, then problem from X times A to compute X to find one X is easy, again by linear algebra. There are many X, but to find a short X is very difficult. And so this kind of problem related to lattice problem. If you consider that each column of A like a vector, and here is a linear combination of the vector that give a lattice vector, and the noise is means that we give some point distort from lattice point, and the problem is to find back the closest lattice point. So that is seem a very, very hard problem, even for quantum computers. And so now from the n-gamma, we can have a learning error encryption, we add noise, and you can decrypt. And we can get the mask with some noise, and thus we get the message with some noise. So that's why you can only get the message in a small space, big or small. Because big or small, we add noise is became small. So we can do the bit encryption. And so it relies on two problems that's called CIS problem and LWE problem. That if we do linear combination and we add noise, that gives a signal that is indistinguishable with the uniform signal. And that is very interesting. Also, that it can somehow resist quantum attack, but it can also help us to have additional functionality. Because if the n-gamma for one public key, Y, we have one secret key, X. So that's G to the X equal to Y. But here, we can have many X. That certifies that X times A equal to 0. And so GPV give a pre-sampling algorithm with a trapdoor when generating A. We can generate for one fixed public key many secret keys. And so that's opened the way to multi-receiver encryption. Thus now for one public key, we can give the secret key to many authorized users. It's very important for the satellite transmission that is very costly. We want to broadcast something to a group of authorized users. And so this opens this way to advanced primitive, but it also puts new problem because when the colluding users collude, then they can, from their key can produce a new authorized key. And then they can also create a pirate decoder that decrypt the ciphertext and try to avoid any tracing algorithm. And so to deal with this kind of problem, we need new kind of algorithmic problem. And that gives the new variant that's called the cases and KLW to capture this problem. And for the cases problem, how we can control all the space that can generate by the adversary. And so Bonnet and Freeman give the cases program that if the adversary have a case small key, then they can show that all the key the adversary can produce is to do the linear combination of this key. It means that it's very hard to produce a new key outside of this span of this own key. And for the tracing, in 2014, with Lin's Stanley extension, we introduced a KLWV variant, because now if the adversary have shocked the key, they can multiply this way and get something small. So the LWE signal cannot be distinguishable from uniform distribution, but we show that it can be still indistinguishable from the uniform on a subspace that's orthogonal to all the key. And it's sufficient for us to do the tracing on the malicious user. But now, so it's also in cryptography. When we want to get a new property, we need to propose a new algorithmic problem. And we need to study the hardness of this problem. And so Bonnet and Freeman give a reduction from standard Cs to K-Cs, but the reduction is, of course, exponentially. And so it means that we can only deal with a constant K. It means that we can only have a system with constant number of users. That is not useful, and they put a very important open problem to get a tighter reduction. And so in our paper in 2014, we solved this open problem and give a reduction with a polynomially loss. And so it means that by this reduction, we can have a system with a polynomial number of users. And so all of this problem can reduce from the worst case lattice problem. So that's it means that a new tool can give the tool to, again, strong adversary like quantum adversary, but also can open the way to get more functionality. So now the last party I want to talk. So we have a scheme. I believe that they are secure, but up to now, two assumptions we consider for cryptographic design since the period of Tekhoff in the end of 19th century. That's based on the receiver privacy assumption. We say that the receiver do not leak the secret key, because if we leak the secret key, anyone can use the secret key to decrypt. And the second assumption is about the sender freedom assumption, is that the sender, I can choose, I'm free to choose a message to be encrypted. So both these assumptions are very realistic for normal setting, but fails in a dictatorship. Because in dictatorship, then the authority, the dictatorship here, I talk about the big tech or the government who want to control all the users. And so they can ask each user to give me the secret key. And also they can ask some user to send the message that they don't want to send. And so it means that this kind of assumption could be broken. And how we can deal with this scenario. And it's also this scenario is exactly the current crypto war that we are living in since the year 80, the last century. And so the first thing is that the dictator wants to impose law to weaken the encryption and to add a backdoor in the device of the user. But this will give a huge risk for everyone, and including the dictator. And one of the examples is the Clipper chip. When the US, in the administration of Bill Clinton, they passed a law to allow to add backdoor in the device. But then Matt Blasey, a cryptographer, shows us, give a technical demonstration that if you put a backdoor in your device, then not only you, but your enemy can also get information from your citizen. And so this means that this puts a huge risk for everyone. And so before this technical demonstration, that's this law, and then abandoned. And so this means that to avoid this kind, we need public debate, petition, or technical demonstration to oppose the approval of such law. And now the second scenario is that we suppose that the dictator is smart enough to allow standard encryption. However, they still want to control all the user. remotely, massively, and remotely. And so they allow to do the standard encryption, but then remotely can ask, give me the secret key and ask to send this message. And so to deal with this kind of scenario, so we introduce anamorphic cryptography to provide a way to preserve privacy in this scenario. And just a way why we call the anamorphic is comes from anamorphic art. And so anamorphic art is also two-view principle. It means that there is a two view on the same object, and the object can be seen only from many viewpoints, but only the complete image only appear in the specific angle. And here is the image that I took at the National Museum in Singapore. So the second image, we think is there the Japanese magician here? Okay, so on the second image, you see there is someone here behind the chair, but high the chair. Very, very strange, magic. In fact, the two parts of the chair, this part of the chair, in fact, were put on the back of the room. And only from my viewpoint that these two parts match to form the completed chair. From any other viewpoint, they are separate. And so it means that from one angle, we can see the complete picture. And so that's in art and in cryptography, like we discussed. They also mainly two view, the ring view, like the journalist proof, the actual interaction between the insider, and the simulated view, that the interaction can be simulated by a simulator that don't have the secret. And the security of a scheme is that the ring view is indistinguishable from the simulated view. So in that case, it means that the scheme doesn't leak any secret, because without the secret, I can also simulate the view. And we propose anamorphic cryptography to capture, to combine these two things, anamorphic art and cryptography. And so the goal is that we can have a scheme on the standard scheme allowed by the dictator. We can produce anamorphic ciphertext in such a way that with the normal key, then it will decrypt to the regular message. But the view with the second double key that I generate, and no one knows if I have a double key or not, with the double key, I can decrypt to an anamorphic message. And so in that case, then and we need to be sure that everything looks normal to the dictator. And if formalized by the ciphertext rule, it means that the anamorphic ciphertext should be distinguishable from the normal ciphertext for an allow standard encryption. And the second rule is a key rule that this indistinguishability should be remain honed even for a very strong dictator who can ask us the secret key. Even if the dictator have a secret key, they cannot distinguish between the anamorphic ciphertext and the normal ciphertext. And so it means that even I was controlled by the dictator, I can send a normal looking ciphertext, but is encode in fact another message. And so even if I were imposed to send some message, I can say that it's not my intention to send this message. And the dictator can also suspect about the user and can block some user from the communication. And so we try to formalize this as a blocking rule that we can broadcast many different anamorphic ciphertext in such a way that even almost all of the users are blocked. If one of the users is not blocked, then the anamorphic message can be sent. And so we propose a public key encryption with anamorphic broadcast mode. So here is a standard scheme, and we can hiddenly add another anamorphic broadcast. We produce the double key, and each user gets a double key. And the nice thing is that the ciphertext of this hidden broadcast, anamorphic broadcast, look exactly the same, and distinguishable from the ciphertext as the normal public key. And so this is sent on the public channel, but the anamorphic user can decrypt to something else, not the message in the regular scheme. And so what we do is a generic method we have a method to turn the anonymity to anamorphism. And so if we have a public key, which associated anonymous multi-channel broadcast, it means that you can broadcast to different group of users, and we can hide the identity of the user in each group. Then from this, if the ciphertext of the two schemes look the same, then you can have an anamorphic broadcast. And so the construction based on series sequence of our work, first with the multi-channel broadcast, with my first PhD student, Jing Kuang, in 2012. Then we proposed multi-receiver encryption, and then finally with anonymous broadcast encryption in 2020 with Dawson Pine in the room and multi-use. And then we generalize this to multi-channel. And the idea is that we based on KLWB assumptions that we introduced before, but now we turn the tracing signal into the broadcasting ciphertext. This means that if we want to send to a target set S, then we will sample in the subspace as orthogonal to this key plus noise. And so you can see any user in S, if they multiply with this signal, then they will get something small, and they can demask to get the message. And we generalize this method to multi-channel. Thus, we partition the target set into subset, and we add information into each subset in such a way that all the user in the same subset will decrypt to the same thing. And from this, we can get the anonymous multi-channel broadcast encryption, and by our generic method, we get the anamorphic broadcast. And so this notion is currently, there are many groups across more than 10 countries have been developing this concept of anamorphic cryptography. So in US, in France, in Switzerland, and to develop many different notions of anamorphism and robustness, the extension, even in the anamorphism in other primitives like in signature, fully homomorphic encryption, or in voting, public key anamorphism, where we do not need to share any double key. So now I want to conclude. So my personal expectation is that in the coming year, in the future, technically, we can show that the privacy and the utility can go hand in hand. Many people say that to get the utility, then we cannot protect privacy. We need to take all the data. We need to do the AI on all the clear data, etc. But my position is not true. If we look back in the year 80, then cryptography, people also say that communication, if we encrypt the communication, it's too expensive, it slows down the communication. The people don't want to encrypt anything, but with encryption, and now we know that with encryption, only with encryption, that we can do many things. We can exchange with the bank, we can have an email, private email, because if anything is clear, so we cannot have this kind of application. It means that encryption not slow down the communication, but the technology will develop in such a way that is transparent. But it gives new utility. It allows us to exchange, to buy online, to do all the activity online now. And I think that privacy now is exactly in the same situation. We can, in the future, only applications that protect our privacy will have an advantage in the concurrence. All the applications that take our data will not survive. And so we need the proof of protecting the privacy, I think, in all the applications. And so also when the people care more about privacy, in the government and organization will be more committed to ensuring the privacy. And we also, in our paper with Moti and Persiano, we also put a meta conjecture for anamorphism is that for any standard scheme, is a technical demonstration of the futility of the dictator Dinh Hèn. So if the dictator are strengthening, that does not give advantage for the dictator. And so there's no sense to put people in a dictatorship. And I also really like to quote a Broadway for the cryptographic community, not for all the community, of course, but the cryptographic community that they place for a invention of our disciplinary culture to attain not only personal mass, but also for the societal implication of our work. And so if we develop some application, then we need to think about the impact. For example, we need too much data, personal data, or not, and which kind of data we can collect, which kind of data we cannot. So you see, so in the society, there's a different kind of interaction between the citizen and government, and citizen between the individual. And so for the interaction between the citizen and government, then I think that the government can collect some kind of data like on our passport, the name, etc., and put the technology to improve the public service. That is good. But for the other kind of interaction between the individual or individual, there's no reason to collect all this kind of data. Especially, there is no reason to collect our ADN or something like that. It's very dangerous, especially if it's has been leaked. So it's very dangerous. So we need to think about all this kind when we develop something. Which kind of data we can collect, which kind cannot, and which technology we need to develop to protect the privacy. So in the coming year, I think that this is some research team. In cryptography, that's important is to reduce the need for trust in the authority, how we can do the decentralization, that we do not need to trust any authority, and to do the computation over encrypted data so that we can delegate our data, but in an encrypted way, in such a way that we can exploit the advance in technology, but we can also protect our privacy. And also to, again, the strong adversary and to achieve a post-quantum security, and also do the privacy in AI, including that how we can use AI for good, for enhanced security. And also to need to consider the society implication of our research work. And here is the time, okay, opportunity for me to thank also my co-author in the work that I mentioned in this work, and many of them are here, like Hoa, Lee, Tang, and Moti, and so. And also I thank you all of you for attention.
Thank you for the wonderful lecture, and also like to give us that you can believe in our future, right? Now, any question?
I also big thank for your wonderful lecture. I don't understand much, so I have only 3 questions. At first, it's at the beginning of the lecture, you told about something to hack to compute. So, can you explain what is the hack to compute? This is the first question. The second question is, you also said that the cryptography will be appear where we have some things in one way it's easy to compute, and the another way is hard to compute. For example, if we take 2 numbers and multiply, get the product, it's okay. It's very easy. But if we have the product and we have to find the factors, it is hard. So what can we call this situation? This second questions. The third question is when you mentioned about Shaw, Peter Shaw, who I think this is avant-garde in quantum computation. So recently, I had a short talk with Professor Nam Thanh Sơn, who is a very famous physician. And he said about the quantum computers. He said that this is very far, that we can build this computer. And the problem is about quantum error correction. So I want to know what is quantum error correction and why it is hard to build. This is my third and the last question. Thank you.
Okay, so I need a memory to to remember your only three questions. The first question is how is to solve the problem. So like the first slide I say, the how is a computational view. And we are in mathematical view. And the how is a computational view, how they can use the computers to solve the problem. The discrete log problem, which they use the classical computers, they cannot solve, but if they use a quantum computer, they can solve. So it's a how is to solve the underlying mathematical problem with the computational power. And so the third question, yeah, it's exactly the Nam Thanh Sơn says that it's very, very far. And that's why my position is that it's very unclear. We should not invest hugely in constructing this quantum. And why you see the quantum state is very fragile. And so to maintain the quantum state is very costly. And if the algorithm takes about 100 days, with all the problem of decoherence, the stable, then it's very difficult to maintain the state. And also when we do the measurement, it means that we do the photon, and then it puts noise. So what we measure is not exactly. It means that there is error. But the difference with the classical error correcting is that in the classical error correcting, we see on the data, we see on the bit. And our goal is to correct it. But in quantum, we see nothing until we do the measurement. It seems like in quantum, there's also two view principle. Until before we measurement, it's like wave. And then when you do the measurement, it's like particle. And so until we do the measurement, we don't see anything. It means that we need to do correcting error in black box. We don't see anything, but we need to correct the error. That's magic. And so that is very difficult. And that's why we need advanced method, like Google developed a surface code, a different type of code that even we don't know the data, we can correct error. And so that's why it's very costly. And so that's why we need many physical qubits. We need to prepare many physical qubits to correct something in black box. And so until we do the measurement, we can get the exact result. And so that is why it's very hard. And so that's why it's totally different between the logical qubit and physical qubit. Logical qubit is in theory, a physical qubit is in real life. And we need, so that's why we need machine with million qubits to run a machine theoretically with some thousand of logical qubits. And that's why it's very different. And the second question?
About two ways operation.
I use a quantum machine to predict your question. And in fact, here's the situation. We need to have a model of computation. And so the one way, here is the definition of NP complete, and here's the definition of one-way function. And so one-way function is something very efficient to compute on a random input. And it's very hard to inverse on random input. Right. Yeah. And it's a randomized function, it's a random input. That's different from P and NP. P and NP is the worst case hardness. And for cryptography, we don't protect one specific message. We need to protect all the messages. That's why we need an average randomized function. And that's why we cannot rely on any NP complete problem. We need to specific problem. And actually, there is a separation between one-way function and P and NP problem. There's different things, very, very interesting to classify the problem. And that's, yeah, define many worlds where P and P different, where NP, there exists NP hard problem, but there does not exist cryptography, and there is a one-way function, but there does not exist a public key cryptography, and there is a world with public key encryption.
Thank you. Very clear.
I have two questions, not three, but two questions. So the first one is, do you have proof of the property of anamorphic inscription that you claim? Do you have mathematical proof of these properties?
Yeah, we prove that based on our K and W assumption. Okay. And this is reduced to the standard NW assumptions that's based on all the lattice-based scheme.
I see. The second question is a bit of provocation. If it is not possible to do, no, it's very difficult. It sounds like impossible to do the quantum computings. Why do you care about quantum proof encryption?
Oh, because we care about the small probability. And the problem is that maybe now, up to 20 years, there's no quantum, but now there's many important data that should be hidden for 50 or you want to?
No, I think about it differently. So until quantum, we only have factoring and discrete log. Now we have lattices and more. So more mathematical structures that can support cryptography. Even forget about the quantum computer. It's a good excuse to investigate take a mathematical structure and try to find hardness that helps cryptography.
That's not the answer.
Yeah, I don't care about quantum
theoretical.
Thank you.
It justifies the theory.
Yeah, the theory. We can have we can have more interesting without quantum, but because of quantum. But one of the problems is hard rest now and decrypt later. Hard rest now, there's many people who collect all the data now and wait 50 years. If one day there's quantum, they can decrypt the data now. And so even the probability is small, we need to predict that. And we predict that by developing the sample scheme. No deal with quantum. So it's extra probability to have a post-quantum security with the standard mathematical structure.
Like geometry of numbers to be used for cryptography, regardless.
Yeah, I think Professor Châu question remind me of the hack that we had one time in Princeton, and I saw somebody with a shirt saying, "If the war come tomorrow," so maybe they are preparing for the war. I have another question. So I think that when you talk about post-quantum security and many things, so you rely on the hardness of the problem of finding the shortest vector in the lattice, right? So what is the typical dimension of the rank of the lattices that you are looking at?
Oh, its dimension is some hundreds. Yeah, and so it means that the matrix is some hundreds. And in fact, here is I also have yeah, if you want to. So on this problem, we somehow realize on shortest vector problem. And why we need the dimension is quite large, because in the worst case, if you want to find really the shortest vector, it's an NP hard problem. But as I said, it cannot be used directly for cryptography. In cryptography, you need to use something in the factor here. It's polynomial on the shortest vector. And in this zone, you can do cryptography and you can have a nice reduction. But then we need to pay the cost that the dimension should be large. And so in practice, it's 700. And so it's the drawback of this kind of scheme exactly that the public key is quite large because the dimension is 700, but with the new technology, so is very feasible. And Macron already sent to US government message using quantum secure scheme.
So, you know, like in group theory, we have a famous lattice of dimension 248. And we know that the shortest length is like 10 or 12, but we cannot prove it. So maybe like not to find any short effect, but just to know what the minimum length, so we don't know.
Yeah,
Right.
That's a hard one.
Right. Any further question to Professor Hieu? If not, let us thank Professor Hieu and all the 5 speakers of the today meeting for the wonderful lectures.
Thank you very much.
And I think we should also thank the institute and the organizers for all the work that they put into to have this wonderful meeting.
So may I, well, before I give a conclusion of the meeting today, may I add one more explanation of why we need to study quantum proof cryptography? The reason I think is because maybe the alien, you know, they already have quantum computers and we have to be ready. So, so I think that's more, that's a better reason. So anyway, so this is the conclusion of our 2025 annual meeting. And on behalf of the Vietnam Institute for Advanced Study in Mathematics, on behalf of Professor Ngo Bảo Châu, I would like to thank you, the speakers again, for the wonderful talks. And also for the 2 wonderful chairs of our morning and afternoon section, Professor Phan Nam and Professor Phạm Hữu Tiệp. And thank you all for being here from the very early morning until now. So thank you so much and see you again next year. Right. So for those of you who are coming to the embassy, then there's a car waiting outside, and we can take part from now. Yeah. Dạ vâng, đi luôn.